Welcome to Chapter 8 of the Universe. The foundations, the variables, and the structure of the universe. Physical world versus mathematical world. A foundational inquiry. The central question of this chapter is simple. What comes first in our understanding of nature, the physical world, or the mathematical description of it? This book begins with a clear answer. Nature is primary. Every true understanding of the universe begins with nature itself. Not with equations, not with diagrams, and not even with models, but with the observable and sensible phenomena that confront us. As Leonardo da Vinci is quoted in the chapter, nature is the mistress of all masters. The journey of natural philosophy therefore begins by looking at what is, before asking what can be calculated. Without this grounding, even intelligent mathematical work can lose contact with the physical world. But this does not mean that mathematics is unimportant. Quite the opposite. The chapter recognizes mathematics as a necessary tool for clarity, precision, demonstration, and communication. Leonardo da Vinci is also quoted as saying that no investigation can strictly be called scientific unless it admits of mathematical demonstration. The point is not to place mathematics above nature. Once nature has been observed and understood physically, mathematics becomes a powerful instrument for expressing what has been found. Mathematics can express physical relationships, test them, compare them, and extend our reasoning. But mathematics does not generate the physical phenomenon itself. The scientist must first grasp what is physically happening, and only then express it in mathematical form. This distinction becomes especially important when the order is reversed. The chapter warns against treating equations as though they came first, and nature followed them. It also warns against treating models as more real than the phenomena they were designed to describe. A mathematical curve may represent an observation. An equation may summarize a relationship. A model may organize many observations. But none of these should be confused with the physical reality they represent. The laws of nature are born from physical observation. Consistent behaviors are observed across different conditions. They are tested repeatedly. Only then are the regularities formulated as laws and expressed mathematically. The chapter gives familiar examples from physics. Collisions, pushes, falling bodies, and the observed attraction between bodies provide physical experience, from which mathematical relationships can be formulated. Without the experience of weight, or the sight of a moon in orbit, there would be no physical observation from which those mathematical descriptions could arise. Mathematics can refine truth, but it cannot invent the phenomenon. The danger becomes greater when mathematics overshadows nature. The chapter considers the possibility that we may begin to see equations as truths before evidence, models as realities, and experiments as things to be adjusted to fit theories. That would reverse the proper relationship between nature and mathematics. Nature should not become merely the stage upon which mathematics performs. The physical world must remain the foundation. The chapter then turns to the unity and complexity of nature. Reality is presented not as a collection of isolated equations, but as a totality of interactions, balances, and tensions. Mathematics helps us simplify these relationships. But simplification must not destroy the unity of the physical system. The goal is to find simplicity within nature's harmony, rather than impose simplicity from outside. The chapter uses a particularly useful analogy. Phenomena are the letters of a script. Natural laws are the words. Mathematics is the grammar used to write them. But the script begins with the letters of nature itself. In other words, we must first observe the physical world. Then we identify consistencies. Then we test them. Then we formulate laws. And only after that do we translate those laws into mathematical form. Finally, we return again to phenomena and ask whether the mathematical description remains faithful to nature. This gives the chapter its rightful sequence of scientific understanding. Observe phenomena as they appear in nature. Analyze consistencies and differences. Design experiments to test those consistencies. Formulate principles and laws from repeated verification. Translate them into mathematical form for clarity and communication. And then return once again to phenomena for testing and confirmation. The order matters. If mathematics or models are allowed to dictate what phenomena must be, we risk replacing reality with an elegant construction. The purpose of mathematics is not to command nature, but to help us understand and communicate what nature reveals. The conclusion of this chapter is therefore concise. Mathematics is a region of necessity. Nature is a region of truth. Mathematics serves. Nature commands. When they are kept in their rightful order, they work together. Phenomena provide the seed and soil. Mathematics becomes the instrument through which the relationships discovered in nature can be expressed with precision. With this foundation established, we are ready to move to the next question. How should observation itself be organized so that scientific understanding develops in the correct sequence? That is the subject of Chapter 9. Observation and Sequence of Scientific Understanding. Thank you for joining this chapter of the universe. The foundations, the variables, and the structure of the universe by Sayed Mustan Wali.